Hello and good evening, or whatever time it might be. I got a request for something, and I think this might be a good idea to talk about right now, because it is kind of a combination of things that we've talked about in the past, and bringing them all together might be a good idea. So the request was to talk about the different types of bonding and how they relate to the periodic table. So I made a video that talked about ionic bonding and covalent bonding. But because I have this periodic table here, we can look at this and really just get some chemical intuition going here. And part of this is understanding some of the aspects of the periodic table. We don't have to understand all of it, of course. There's a lot there. But just some of those relevant aspects of it that will help us gauge when we look at a compound. Is it an ionic compound? Is it a covalent compound? Or is it metallic? Or maybe we're just trying to predict, given a combination of different things on the periodic table, how might it bond together? So, first, let's just take a look at the periodic table and think about what it means. What is this telling us? And so first, as an overview, all of these elements, they are referring to specific atoms. And each of these, all elements, they all have protons. Those are positively charged particles that are in the center in the nucleus. And then around on the outside are electrons that are negatively charged. The nucleus also can have some neutral particles called neutrons, but we'll just be focusing on the protons and the electrons, because that's where there's the positive charge and the negative charge, and how those attract each other, and how it affects how elements come together and how they interact. And honestly, if I had to describe chemistry in its most fundamental form, we are truly most interested in what the electrons are doing. The electrons that are more on the outside of the atom. Because that's really where the interactions are going to happen between atoms. And that's where electron sharing might happen, or electrons might be exchanged or transferred, I should say, from one element to another. So, the periodic table is organized in a very specific way. And one thing we might notice is that they're numbered, usually somewhere on the top of the box. 1, 2, 3, 4, 5, 6, etc. Okay, in rows like this. And that's called the atomic number. So for boron, for example, the atomic number corresponds to 5, which means boron has 5 protons at its core. And that is specific for boron. Any element that has 5 protons is, therefore, by definition, boron. Electrons can come and go, but if there are 5 protons, it is boron. Okay. So that numbering system usually goes along with the mass. So the mass is the number down here. But it doesn't always go in order. There's a few places, like right here, cobalt, 58.9. This is how many grams are in a mole. And then it goes down to 58.6. So it doesn't always increase. That was confusing for scientists way back in the day. But now we know that it's this number of protons is the way that we line them up in the periodic table. So, how about the columns? Why are they stacked in this way? And that has to do with the reactivity. And the reactivity is related to the number of electrons that there are in the outermost shell of the atom. So you can imagine if we wanted to simplify the structure of the atom in a way that's not 100% accurate, but it works to explain some things. We could imagine an atom as like an onion. Now layers of an onion, layer upon layer, and the outermost layer, we call that the valence shell of electrons. And if we look at this group right here, this column, these elements all have 7 electrons in their outermost shell, that outermost layer of the onion. And something that chemists recognized a long time ago is that there's a particular stability that elements have when they have 8 electrons in their outermost shell. These, well, helium's an exception. It only has 2 electrons. But the rest of these, neon, argon, krypton, xenon, radon, these all have 8 electrons in their outermost shell. They're very stable. So these are called the noble gases, and they're extremely unreactive because they're so stable. So these elements, which are called the halides as a group, they have 7. And so they become more stable if they gain 1 electron to become 8. So, in other words, fluorine has 7 electrons in its outermost shell. And when it gains 1 electron, it has the same number as neon. It has gained 1 electron, and so it is fluoride, or F minus, has a negative charge when that happens. One way that it can happen, that electron has to come from somewhere, right? Electrons aren't just flying around everywhere. So one place it can get that electron is from another element. So we want to find an element that will, instead of gaining an electron to become more stable, perhaps there are some elements that lose electrons to become more stable. And indeed, that is the case. And that is the case especially for the elements all the way over on the other side of the periodic table. So if we look at group 1 here, lithium, sodium, potassium, these all have 1 electron in their outermost shell. So if they lose that 1 electron, then the second layer just underneath that top layer, that layer does have a full shell. It does have those 8 electrons. So for example, if sodium were to lose 1 electron, because notice here it has 11 protons, and that means it has 11 electrons total, but it only has 1 electron in the outermost shell. So all these electrons that it has are all layered. They're in different shells. But if it loses that 1, then it ends up with 8 in its remaining outermost shell. So if sodium loses 1 electron, that means it's positively charged. Fluoride, if it's negatively charged, then we have 2 ions, negatively charged, positively charged, that attract each other. Opposites attract in chemistry and physics. So that is the basis of an ionic bond. When you have something that's positively charged, that will usually be a metal over on this side of the periodic table, combined with a nonmetal that's over here on this side of the periodic table. That's where you are most likely to see ionic bonds, a combination of those two. A metal positively charged, non-metal negatively charged. Okay, so that is ionic bonding. And maybe I'll write this part down. So this is, generally speaking, what we see. Ionic bonding. Okay, so usually metal. That's a positive charge. And nonmetal. That is negatively charged. In the example that we looked at, that would be sodium that lost an electron. And then our example of a nonmetal was fluoride that had gained an electron, so it's negatively charged. And together, we could say, oh, let's combine those. And that would give a compound, sodium fluoride. Now these would be 1-to-1 ratio because sodium is +1 charged, fluoride is -1 charged. But if instead, let's say we had an aluminum that was +3 with oxygen that's -2, we would need to balance out those charges to give a neutral compound. So the way we do that, or I should say the way aluminum oxide does it, is that you have 2 aluminum ions and 3 of the oxygen ions. So I should probably put a 2 there, right? Oops, 3 I mean. X that out. And a 2 goes there. Okay. Alright. So that's what we see with ionic bonds. And that's typically from the periodic table that we're combining them from 2 different sides of it because of those tendencies. The tendencies that the nonmetals have. There's really not that many nonmetals compared to all the metals. All these are metals. All of these. All of them. And there's the cutoff, essentially. It's this diagonal line here, because these are also metals. So we just have a little triangle here of nonmetals. Okay. So, in terms of covalent bonds, this is where we get a lot of different combinations of the different nonmetals together. Okay. And this is where we have 2 or more nonmetals. And they're sharing. So that's how they're getting their octet. When I say octet, I mean 8. That's how they're getting their 8 electrons. So if we look at oxygen, for example, oxygen has 6 electrons in its outermost shell. But 2 oxygens together, they can share their electrons so that they both end up with 8. So if we have an oxygen with 6 electrons in its outermost shell, I'm showing each electron as a little dot. And then along with another oxygen that has 6. So all together they're sharing here 4 of them. That way this oxygen has 8, and this oxygen also has 8. So there's many, many different ways that lots of these nonmetals can share electrons together to form a good number of compounds, especially carbon. Carbon has 4 electrons in its valence shell, in that outermost shell, and that allows it to bond to itself in chains and with hydrogen, as well as with nitrogen, oxygen, halides, sometimes phosphorus and sulfur. But there are literally millions of carbon-based compounds out there once you combine them in all these different ways. So that's why the study of organic chemistry is so enormous, because there are so many different compounds and ways that these carbon-based compounds can react with each other. So it's pretty fascinating how organic chemistry, being based on one atom, is so big. On the other hand, inorganic chemistry is essentially the study of pretty much everything else on the periodic table. So, and that's also an enormous field. And there's lots of studies of how these metals can be in biology, biological systems, like how in our bodies we have iron that's in several different proteins and enzymes and helps us with metabolism. We have cobalt, we have copper, we have zinc. There's so many of these metals in our bodies and biological systems. They're also really important in the environment. All of these play different roles in the environment. We have some that are necessary for the environment, such as calcium. Calcium carbonate is a natural buffer for aqueous systems, for lakes and rivers, ocean. And then on the other hand, there's things like mercury or lead. And when they get in the environment in too concentrated of amounts, then that can be very harmful for those creatures that are living, or for the other creatures that are eating the creatures, because those are toxic. And then there are some really fascinating materials that we can make. Semiconductors, such as those with silicon, germanium, arsenic, antimony, gallium. A lot of these elements right around here, these are on the border between nonmetals and metals, and they have very unique properties on their own. And this is especially silicon, but combining a lot of these other elements, we can make semiconductors, and we can make different semiconductors that can behave in different ways, such as the kinds that we use in computers, or some that are in solar cells, some that absorb light from the sun and give us electricity. Or conversely, if you run electricity through some semiconductors, light is emitted, as we see with LEDs, light emitting diodes. So many other amazing things come from different combinations of the elements on the periodic table. One last thing, a type of bonding would be metallic bonding. And that's essentially what we see when we have either an element by itself, like if you have a piece of iron, it's just pure iron. Those are neutral atoms that are all packed in closely next to each other. But you can also melt these atoms of different metals together, mix them, and then you have this homogeneous mixture, or in other words, an alloy of different metals together. So if you want to have something that's metallic, but it has a certain property, you want it to be extra hard, or you want it to be softer or less dense, or maybe lighter. If you want it lighter, maybe you'll go with titanium. Or if you want it to be very strong, you could put in molybdenum. Iron works well too, especially if you have iron. And in between the iron atoms, you can fit tiny carbon atoms. And that way you get a little bit more hardness. It's not quite as malleable. Malleable is where you hit something and it puts a dent in it. But if you have iron that has carbon in it, then that adds hardness to it. And that is how you get to stainless steel. So much more. I could go on and on. And I will, because I will keep making videos as I do. So, thank you for that request. I do hope it was helpful. And I feel like this was a little bit unusual because I didn't do a lot of writing today. But I just had so much to tell you about the periodic table and elements and applications and how it ties in with bonding. And yes, so cool. All right, well, thank you. Thank you for listening and watching and subscribing. And be sure, if you subscribe, also if you you hit that little bell, and then it tells you when I upload a video. I don't have a schedule yet, so sometimes it's helpful to have the bell to alert you when my video goes live. Thank you. Thanks for being here with me, and be sure to let me know if you have requests. I love getting requests, and I am trying to fulfill them all. There's still quite a few that are on my list, and I am getting to them as soon as I can. So thank you, and I will see you again very soon.